Hello, I'm Donghun Lee from Korea University. I thank Andreas and other organizers for the invitation, and this is really a wonderful conference. So in this talk, I'm going to explain sensing strain and magnetic field with quantum point defect, especially diamond and V-center. So this is the outline of my talk. After some brief introduction, I will spend the first half of my talk the strain field sensing with diamond mechanical oscillator, and then the later half of the talk, the magnetic field imaging with diamond scanning probe microscopy that you heard from Enya. Okay, so for the introduction, for me, quantum point defect is a quite interesting system because this is an atom inside solid. So in a perspective of this defect, it's like an atomic system, so it has a very good property that atoms has. But in the other sense, if you look at from the host material, it is a solid. Okay? So it's can do fabrication and maybe scalable. Not only this fabrication, maybe we can utilize the intrinsic property of this host material. For instance, if you use 2D van der Waals material, maybe we can utilize the property of the host material itself. So I think that's why, for me, it's an interesting system. And from defects in diamond to the recently found some defects in 2D-dimensional materials, there is a variety of this candidate for quantum point defects. Even though today I'm going to focus on diamond and V-center, they all develop quantum information and sensing methodology or technology in this, based on V-center can be potentially applied to these defects, a newly found defect in the future. So I think this area is for me quite promising research field. And this table summarizes sensitivity of MV center to a variety of different physical properties from magnetic field, electric field, strain field, and temperature, and so on. And the size is quite small, and then it can detect from DC to gigahertz frequency, and it can work from room temperature to cryogenic temperature, and also there's some other advantage potentially used in a biosystem or condensed matter system. So it's quite an interesting system. And because of that, it has been already applied in various different sensing research. For instance, we already heard very nice talk. The previous speakers can be used in a sensing a biological system and also condensed matter system. And it can also sense temperature, electric field, strain, and also other some physical properties. So in this talk, I'm going to focus on two research topics, the strain field sensing and magnetic field sensing. And I will give some introduction of this research along these topics, and then our recent activity at Korea University. Okay. So the first one is strain field sensing based on diamond mechanical oscillator. And these are the graduate students involved in this project, and we have a very close collaboration with Enya Jaich at Santa Barbara, and also Dr. Sang-Yun Lee and Seung-Woo Chun at KIST in Korea. Okay, so for sensing point of view, MB Center has been used to prove the motion of mechanical oscillator either through the modulation of the magnetic field from this tip, or through the strain change of the lattice. Okay. So these are just the Honeycomb measurement, and you can see there's some additional phase due to the motion of this mechanical oscillator. Okay, so you can see this collapse and revival of the Honeycomb signal at the period of this the oscillation of the mechanical mode, and also this has been used for pressure sensing and then imaging profile in some material, and also been suggested to sense force. Okay. This is a sensing example, but we can utilize this strain to actually control the MV center. So this is the work at work of Anya Zajce, Santa Barbara. Basically, they applying this strain to shift the zero phonon line of MV center. Basically, you can see the bare optical frequency, transition frequency, shifted and split it depending on the amount of strain you apply through this diamond mechanical structure. So this, if you continue this control, basically the MV centers are not identical because they have a different local environment. So if you look at these data, the MV1 and 2, they have a different the energy of this optical transition. And if you can selectively apply this strain field, you can tune the energy and match to the energy of the other emitter, so you can realize some indistinguishable photons from these pairs, so which can be useful in quantum information application. And so you can apply strain to energy tune or polarization tuning. Okay. You can also use to control the spin property of the MV center. Here's the work from Patrick Valentinsky at U of Basel. Basically, the MV center is linearly sensitive to the magnetic field noise, but once you drive strongly with the mechanical motion and you generate mechanically driven dress state, now the MV state is quadratically sensitive to the magnetic field noise. So what that means is it's less sensitive to the magnetic field noise, so that by using mechanical motion, you can extend the coherence property. Okay, they call the coherence protection scheme. And also their recent work is this. As Anya explained in her talk, 0 minus 1 or 0 plus 1, you can apply this microwave at these frequency. But the transition between plus minus 1 stays magnetically forbidden. But if you apply electric field or this strain field, you can basically directly manipulate between plus minus 1 state. So what they did, actually applying 2 microwave tone and strain field, basically make a closed loop. Okay? And by changing relative phase between these 3 basically control tone, you can actually dynamically control their coherent population properties. Okay? So the MV center can sense motion, force through strain field, but also strain field can be used as another control knob to control this defect center in the diamond. But so far, these are all based on just a single mode of mechanical oscillator. So in our lab at Korea University, we like to extend this to further. So this is probably the first equation that I'm showing in this slide. Actually, if you look at the Hamiltonian of the MV center, the spin state is quite complicated. The strain is a tensor. There's a 6 independent component, and they contribute in a different, they have different contributions. So certain strain component only shift, but the other component is actually split and mix these state. So, but using only one single mode, it's hard to control them independently. Okay, so what if we use multiple mechanical mode? Then can we control this strain component? And as I showed before, the coherence protection with the mechanical mode, maybe can we apply that with the multi-mode, and maybe we can control the population dynamics using multiple mechanical mode. That's the motivation of this work. And so the idea is using these structure, which has a flexure mechanical mode as well as torsional mode. So probably flexural mode is tuning probably this diagonal component, but then this torsional mode generate large shear strain, so maybe used to control the off diagonal term. Okay? So for this project, we have a collaboration with the KIST, and then they fabricate this nice T-shaped cantilever. And so this is the Honeycomb measurement with the torsional mode. Basically, we basically shake this at frequency of torsional mode, and these all collapse and revival features that due to the phase accumulate through this motion of torsional mode. Okay, so at the moment, we only check a single torsional mode, and the next step is actually simultaneously applying these two modes so that whether we can control the strain environment independently. Okay. Right. So I think then now let me move to the second part of my talk, which is the magnetic field sensing and imaging with a diamond scanning probe microscope. So this is a student involved in, and again we have this diamond probe from ENIA, Santa Barbara, and also we have some sample collaboration for magnetic samples. So diamond MB center is a good magnetic field sensor and detect from the DC to up to, let's say, gigahertz this magnetic field. So depending on which magnetic system you want to study, you can basically selectively choose this, different this control methodology. For instance, Ramji for DC magnetic field and dynamical decoupling for AC magnetic field. So to image magnetic field, basically the easiest way is basically you repeat this sensing measurement over many MB center around this magnetic structure, which is basically the easiest way but most time-consuming way. And my students show that we also constructed this wide-field view setup to have a better imaging and faster imaging and better image. But if we want to study small magnetic object with a better spatial resolution, let's say order of tens of nanometer, it's better to have this approach with the scanning probe microscopy. And we already heard nice introduction by Anya. At the end of the diamond atomic force microscope, position this MV center, then scan over interesting magnetic sample, you can image local magnetic field with high spatial resolution. And already within the last few years, this field is actually growing really fast and have been applied to study various interesting condensed matter system. So we like to do this too. So we have this scanning setup. Basically, same under the confocal setup. Now our sample can scan three-dimensional with high spatial resolution. And at each point on the surface, basically we measure this Zeeman splitting in our optical spectrum. Okay? And this is the optical view our setup. This is a microwave wire, and this is the sample underneath. And this is the probe. And we have two different types of probes. One is the probe from ENIA, and the other is some commercially available probes. But the result I'm going to show today is mostly with this probe from UCSB. Okay, this is the SEM image of those setup. So with this setup, we like to test and study two different types of sample. One is some device, current device, and the other is magnetic sample. So in this case, we have some platinum wire, and we like to measure, image the current-induced Oersted field. So basically, once you flow current, once you look at this, there are two wires. Current is flowing this way, and current flowing the opposite way. So they generate different signs of Oersted field. And once you image, you can see the different signs of this magnetic field. And once you, this is a cross section. Once you change the direction of current, of course, the sign of this Oersted field flipped. Okay, and actually, the reason of this shape is because we are sensing only the magnetic field along MB direction, and so once we know the MB direction and simulate this, it quite agree well. So basically, if you're imaging this U-shaped area, you see the change of the sign of magnetic field because the current is changing flow. And if you measure the same area with a different MV center with a different crystal direction, you can image different field component. Basically, combining these, you can get vector magnetometry. So this is not very interesting current device, but we like to image this first and then move towards more interesting sample. For instance, some spin accumulations. Okay? The second example is a magnetic sample. And this is also quite well-known sample, which is the Homology magnetic sample. And from this optical, magneto-optical curve effect Mach image, you see there's some domain structure inside the square shape of the homology. And depending on its size, you can see different domain structure formed. And also you can see this vortex. And this is our simulation of this structure. And so this is Mach image, and we try to image the sample with our diamond sample. And as I mentioned, that we are not imaging this field like a Mach image. We are imaging the magnetic field component along our MV axis. And this is the simulation, and this is our actual image with the setup. And you can see it agrees quite well. Okay. And so this is a simulation, and this, we can image this with two different modes. One we call is a full ESR, and the other is a double ESR. Basically, the full ESR is done this way. At each point, you measure basically this. All the MR signal is a function of full frequency span, and then just plot the splitting of the peak. But which this method takes quite it's a time-consuming method, and there's another way you can do is called dual map. It is basically same as the contour image that Enya introduced. In her case, she just get this contour map as fixed microwave frequency. But if you get this contour map at two different microwave frequency and then subtract them, basically you get very much the same image with the full ESR map, basically. Okay. So there's just there's a different imaging mode you can try. And so by applying external magnetic field, the domain evolve so that you can see once you apply the magnetic field in the minus y direction, you can see that this right-hand side domain grows, and then therefore the vortex can move to the left. And this is our simulation, and this is the measurement, the double ESR contour measurement, and it's quite agree well, overall shape, and also the motion of the vortex. Okay, so this can be used to study this magnetic sample with zero to non-zero external magnetic field. But so far, this is all static magnetic field imaging. Okay? Can we measure some AC magnetic field? So this sample is actually can have ferromagnetic resonance at gigahertz range. So the previous image we showed just the static magnetic field imaging, just basically from measuring this Zeeman splitting, static Zeeman splitting. But this sample, we actually apply 3 gigahertz microwave to realize the spin transition from 0 to plus or minus 1. Okay? And this same gigahertz microwave frequency, this gigahertz microwave can drive the spin texture in homology, which can be the same frequency. So basically, in addition to this perpendicular microwave, there's some perpendicular microwave component from the sample. Okay? And these can be combined and affect our Rabi frequency. So previously, people put nanodiamond on homology disk, and what they found that the Rabi frequency can be changed because of the additional frequency from the sample at gigahertz. Okay? So we basically, but they just can do this only one single point. We like to do this over a whole sample. So we want to image gigahertz oscillation from the sample. Okay? So because we're driving microwave a few gigahertz, it basically drives this spin in the homology sample, And at each point, we measure Zeeman splitting for DC static field imaging, but also we measure Rabi frequency at each point. And this is the result, and you can see qualitatively very different profile of the imaging. You have a good eye, the shape is quite different, and also at the vortex, this signal is the largest. Okay? So we are still analyzing this for mostly the simulation side, but how these oscillating ferromagnetic signal can distribute over this square homology sample is something we are doing. So the take-home message is this: STM, sorry, because ABS QNS. So this can prove with diamond can because MV center can for the sensing point of view, it can sense from DC to gigahertz, right? It can image. You can get the image from DC to gigahertz range. Okay, so I think that's a quite powerful capability. Okay, all right. Let me do summary. So we using diamond mechanical structure, we can study the strain field, and the next step is to try to using not only single mechanical mode but multiple mechanical mode to have a better, have additional degree of freedom to control the spin of the MV center, and also using this diamond scanning magnetometry setup, we studied imaging DC and AC magnetic field in some current device, and some magnetic condensed matter sample. And here the group, at Korea University, and these are collaborators. Thank you for your attention.
Yeah, thank you.